Let's see some examples of the quantum order finding subroutine of Shor's factoring algorithm. What are the inputs to the order finding subroutine? First, we need n. This is the positive integer that we are trying to factorize using Shor's factoring algorithm. The other input that we need is a guess, and we're going to call this guess a. A has to be between 1 and n, and the greatest common divisor of a with n is equal to 1. In other words, a and n are co-prime. So this is the kind of guess we're looking for. So if we take those two inputs, a and n, the goal of the order finding algorithm is to find the minimum positive integer r such that a to the r is equal to 1 mod n. And we call this minimum integer that satisfies this condition the order of a mod n. In this video, we're going to consider the example of n equals 15. We're trying to use Shor's factoring algorithm to find the prime factors of 15, which are 3 and 5. And the examples of a we're going to use in this video are 11 and 7. You can see that both 11 and 7 are in between 1 and 15. And both of them are co-prime with 15. That means the greatest common divisor of 11 and 7 with 15 is equal to 1. So all of the conditions are satisfied. 11 has an order of 2, and 7 has an order of 4. And you might notice that both of these are powers of 2. So that is very convenient. It's very convenient that the order of both of these elements are powers of 2. But in general, this might not be the case. So we can have r values which are not powers of 2. But in this video, we're just going to see a simple example where r divides 2 to the m. Now let's define what m and l are. These are the number of qubits in 2 registers that we're going to be dealing with when we write down all of the rules in this quantum algorithm. So L is the number of bits it takes to represent 15. So N in general is an L-bit number, and 15 is a 4-bit number. That's because you need 4 bits to represent this in binary. What does this string of 4 ones tell us? It tells us that we have 8 plus 4 plus 2 plus 1. And that sum is equal to 15. And over here we have the representation in base 10. So L is going to be the number of qubits in the second register. The number of qubits in the first register, we're going to choose to be 3. And that value is denoted by m. 2 to the power of m, which is 2 to the power of 3 for this example, that is equal to 8. This is an important quantity. It is the dimension of the Hilbert space for a 3-qubit system. And that is what the first register is. So now let's have a look at step 1 of the quantum order finding subroutine. Step 1 is initialization. We're going to initialize 2 registers. This is register 1 and this is register 2. By convention, we're going to write register 1 on the left and register 2 on the right. Register 1 has m entries over here. So that means that there are m qubits in this register. And we're choosing that to be 3. And we're going to initialize this into the state 0. And that's the same as 0, 0, 0. So all 3 qubits in this first register are initialized in the computational basis state that is labeled by 0. We can write that compactly as a single 0 in the first register. But just be aware that this single 0 is just shorthand notation for a string of m zeros. What about the second register? The second register has L qubits. And we're going to initialize the second register in the state 1. But this 1 over here is not a single qubit. It is in fact L qubits. So to represent this 1, we're going to need a string of L minus 1 zeros, which in this case is 3, And then we're going to need 1 at the end of this string. So we have 0, 0, 0, 1. This encodes the state 1 in this 4-qubit register. So that is the initialization step. That's the first step of this quantum algorithm. Step 2 is creating a superposition. And we're going to create a superposition in the first register. This can be done by applying Hadamard gates to all of the qubits in the first register. And then we get this sum over an index k going from 0 up to 2 to the m minus 1. Because we're starting at 0, we have to subtract 1 from this final value. There's also a normalization coefficient of 2 to the minus m on 2. You can see this quantity of 2 to the m showing up in this expression. That is why it's a very important quantity to deal with. And for the second register, it remains in the state 1. And here we're using the shorthand notation. So this 1 is actually 0, 0, 0, 1. So that is shorthand notation over here. Step 3 is the procedure of modular exponentiation. And modular exponentiation gets us from this state over here to this state. And you can see that the label for all of these states in the second register is a to the k mod n. And this k is the same as this k over here. So this is going to be implemented using a unitary operator. And we're going to define that unitary operator as u, and when u acts on an arbitrary state j, it's going to turn that into the state a times j mod n. So we're doing multiplication by a factor of a mod n. These are the two inputs to the order finding subroutine. We have n and a, and we're using that to define this unitary operator. And this unitary operator has eigenstates, which we can call lambda sub s. And these eigenstates have eigenvalues of e to the 2 pi I s on r. This r is the same r that we defined over here. It is the order of a mod n. So that is a unitary operator which is used to perform the modular exponentiation procedure. And that gets us from this state to this state. So that is step 3. Then we have step 4. Step 4 involves applying the inverse quantum Fourier transform to the first register. So when we do that to the first register, we get this format over here. You can see that in the second register, we have eigenstates, and these are the eigenstates of this unitary operator. And in the first register, we have estimators for the quantity s on r. So these, in general, are approximate values for s on r. And s on r can be treated as a phase. So this is actually a phase estimation procedure. It's a phase estimation procedure which is adapted to the problem of order finding. And when we measure this first register, we're going to get these s on r tildes, these estimators for the quantity s on r. And from that, we can extract this value of r using the continued fractions algorithm. And that can be done on a classical computer. So this is an overview of the quantum order finding subroutine. Now that we have these important stages over here, and then we have defined the quantities of m and l, and we've also chosen our value of n, we can start to actually look at these two examples for A. And one observation that we're going to see when we examine the eigenstates of the unitary operator is that the sum of all of these eigenstates is equal to the state denoted by 1 up to a normalization coefficient. And this normalization coefficient depends on the order. So if we multiply this sum of all the eigenstates by the normalization coefficient of r to the minus 1/2, we're going to get the state 1. And that state is the same state that we initialized the second register in the first step. So those are the 4 steps: initialization, creating superposition, performing modular exponentiation, and then performing the inverse quantum Fourier transform. And then finally, you need to perform measurements on the first register, and you can use the results of those measurements as the inputs to the continued fractions algorithm, and from that you can extract the value of r, which is the order. So the inputs to this algorithm are n and the guess a, and the output is R, the order of A mod n. Let's consider the example of A equals 11 first. So 11 can be written as 1, 0, 1, 1 in binary. What does this actually mean? This is telling us we have 8 plus 2 plus 1. This 0 is telling us that we don't have 4. So 4 does not appear in this representation. We just have 8, 2, and 1. And those values, they sum to give 11. So this is the base 10 representation of 11. And what happens when we square 11? When we multiply 11 by itself, mod 15. We're dealing with modular arithmetic over here. What is going to happen? Well, 11 squared is 121. This is one more than 120. And 120 is 8 times 15. We have an integer multiple of 15 plus 1. So we have 121. And every integer multiple of 15 is the same as 0 mod 15. So the only thing we're interested in is that little remainder. And that remainder is 1. What does this tell us? It tells us that 11 squared is equal to 1. So the minimum positive integer r, such that 11 to the power of r is equal to 1, mod 15, is equal to 2. So r is equal to 2 for this example. And you can see that I'm purposefully writing this value of 1 with 4 bits. We're consistently using 4 bits for all of these values. That's because we're going to be encoding these numbers into this second register. And the second register has 4 qubits. So this is actually the initial state. This is what we're starting with in the initialization step. And we've seen that this is not a very complicated pattern. We just alternate between 11 and 1. So all of the odd powers of A are going to give us 11, and all of the even powers are going to give us 1. Now let's analyze the eigenstates. So if we consider this unitary operator, where A is equal to 11 and n is equal to 15, then these are eigenstates of that unitary operator. And we can call them lambda 0 and lambda 1. So the first eigenstate is a superposition of the 1 state and the 11 state. So this 1 can also be written as 0, 0, 0, 1, and this 11 can also be written as 1, 0, 1, 1. So here we have a superposition, and over here we have a superposition with a relative phase of -1. Where do these states get mapped to? So this 1 is going to turn into 11, and this 11 is going to turn into 1 when we multiply by 11. So that's what this unitary operator does. It multiplies these values inside the ket by 11. And this doesn't change anything because addition of these kets is commutative. So we have an eigenvalue of +1. That corresponds to e to the 2 pi I times 0 over 2. So this 2 over here, that is the value of r, and the value of s is equal to 0. The next eigenstate over here, lambda sub 1, has a minus sign over here in this superposition. So that means when we turn 1 into 11 and 11 into 1, we're actually going to flip the order. And we can factor out a minus sign. So the eigenvalue over here is -1. So if we factor that minus sign out, we can put these guys back in their original place. And this eigenvalue of -1 corresponds to e to the 2 pi I times 1/2. We're going 1/2 of the way around the unit circle in the complex plane. And that gets us to -1. And what if we take the sum of these eigenstates? Well, this plus sign and this minus sign, they're going to cancel, so 11 is not going to appear. And we're just going to have this state 1. And we're also going to have this normalization coefficient out the front. And if we get rid of that normalization coefficient, then we can move it to the other side, and it's going to be this normalization coefficient. So the sum of this and this is going to give us 1, up to this normalization coefficient. So you can see that the normalization coefficient here is 2 to the -1/2. And if we add these guys together, we're going to have another factor of 2. And then when we move that coefficient to the other side, it's going to satisfy this relationship. Now let's consider the example of A equals 7. 7 can be written as 0, 1, 1, 1. So we have no 8 but we do have a 4, a 2, and a 1. So 4 plus 2 plus 1, that gives us 7. Let's have a look at this pattern when we keep multiplying by 7. So 7 times 7, that's going to give us 49. 49 is 4 more than 45. And 45 is 3 times 15. So we have 3 times 15, that's an integer multiple of 15. And then we add 4 to that, and that gets us to 49. So that explains this 4 over here. And 4 can just be written as 0, 1, 0, 0. This is the 4's place over here. So there's no 8, there's no 2, and there's no 1. Let's multiply by 7 one more time. And that's going to get us to 4 times 7, which is 28. 28 is 13 more than 15. So that's where this 13 comes from. And then if we multiply 13 by 7, we're going to get 91. And 91, that is 1 plus 90. And 90 is 6 times 15. So we have 6 times 15, that's an integer multiple of 15 plus 1. And that gets us to 1. So the order of 7 mod 15 is equal to 4. So we have this cycle of 4 values. So now let's have a look at the eigenstates. They're a little more complicated than the eigenstates for 11 because we have 4 values that we're cycling between. So we can consider these 4 eigenstates over here. And the values of S are 0, 1, 2, and 3. So S goes from 0 up to R minus 1. This is 4 minus 1, which is 3. The normalization coefficient is now 2 to the minus 1. That's because we have 4 terms over here. Over here we just had 2 terms, but now we have 4 terms. So we're just taking a superposition of 1, 7, 4, and 13. And equivalently, you could write all of these values in the binary form. And when we actually encode this in qubits, we will encode it as a string of 4 bits. And those 4 bits are going to be a computational basis state. So in this superposition over here, the 1 is going to get multiplied by 7. That's going to produce 7. The 7 is going to turn to a 4. The 4 is going to turn to a 13. And the 13 is going to turn to 1. An observation you can make is that 13 and 7 are multiplicative inverses mod 15. 11 is actually its own multiplicative inverse. So 11 times 11 gives you the multiplicative identity, which is 1. So we have seen what this unitary operator U does to the first eigenstate that corresponds to S equals 0. This eigenstate just gets mapped to itself. We have the exact same state over here. All we've done is moved this 1 to the end. So all of the coefficients are plus 1 in this superposition. So moving them around, swapping the order, doesn't have any effect. That means the eigenvalue is plus 1. But that is not true for the remaining 3 eigenstates. That's because they have these coefficients appearing over here that are not equal to plus 1. We have coefficients of minus 1, and we also have coefficients of minus I and plus I. And these are different combinations of these coefficients, but we still have the same states, and those are 1, 7, 4, and 13. And those states are consistently going to get mapped to 7, 4, 13, and 1. But what we're going to have is different coefficients appearing over here. But what we can observe is that if we factor out a value of plus I for this state, a value of minus 1 for this state, and a value of minus I for this state, we get back the same format that we started with over here. So these values are actually the eigenvalues for these eigenstates. And these eigenvalues are very special. You can write them in this format of a complex exponential. And they correspond to the values of S that are 0, 1, 2, and 3. And we're using those values of S to actually label these eigenstates. So we have lambda 0, lambda 1, lambda 2, and lambda 3. And what is very special is that if we represent this in the unit circle in the complex plane, we're actually going to divide up the unit circle into 4 slices. And we can think of these as rotations, a quarter of the way around the unit circle. So we start off at 1, then we go to plus I, then we go to minus 1, then we go to minus I. And if we were to do one more rotation, we would get back to where we started. That's 1. So we have a cycle of 4 values, just like we have a cycle of 4 values over here. That's because the order of this value a is equal to 4. So that is the minimum positive integer. But note that if we have multiples of 4, they're also going to satisfy this relationship over here. And if you have multiples of these other values, you're also going to see that pattern reoccurring. So it is a cycle. And the quantum Fourier transform is very good at analyzing cycles. So we're going to see these cyclic patterns in the complex plane, and we're going to see these kind of formats over here with complex exponentials. And they're very useful for analyzing these types of patterns. These eigenstates and these eigenstates are going to appear in the next few videos. We're going to write out the full states, all of the bits for this step, that's step 2, and for this step, step 3, and step 4. And in these last 2 steps, we're going to see these eigenstates emerging. These are the eigenstates of the unitary operator that performs this operation over here. It multiplies by a mod n. And these eigenstates appear in this final step over here. And this step is the result of applying the inverse quantum Fourier transform to the first register. And so you can use this video as a reference. You can see where the eigenstates come from, and you can also see their corresponding eigenvalues. And we're going to see the examples of a equals 11 and a equals 7 in the next few videos.